Today we're going to conclude the part on the quest algorithm that we saw yesterday, but in principle we are going to see in detail two of the main sensors for attitude determination, so star triggers and the gyroscopes. I would like to recap a little bit what we have done yesterday, because it was a very long demonstration, and I'm pretty sure that you need to focus on the method that you need to use to solve the quest algorithm. So first of all, I would like to recap what we have found yesterday. So yesterday we have found that our goal was to find minimize this cost function j that represents the discrepancy between our measurements that are given by W and our observed relative orientation of those objects that is reported in the optical bench frame, through the attitude matrix. So what we want to have at the end is that the sum of these squares of differences of vectors should be equal to 0. Of course, they will not be never equal to 0, because there are always sources of errors in W and in V, as we have seen yesterday. We have delta W and delta V. So what we need to do is to find the best estimation of the attitude matrix that minimize this sum that is always positive. So we know that this cost function has to be very close to 0, but it will never be equal to 0. We found out that this minimization consists in a maximization of another function that is a function of the attitude matrix. That is, so we have 1 minus GA. So since J has to be close to 0, we know that GA has to be close to 1. What we have found yesterday is that by using the implementation of the quest algorithm, so what we have done, we express the attitude matrix as a function of the Quaternion. By using this implementation, we were able to demonstrate that this problem, so the solution of the attitude matrix, consists in the determination of a quaternion that satisfy this eigenvalue problem. We also demonstrated that this GA correspond to the maximum lambda, so the maximum eigenvalue eigenvalue that provides the eigenvector of that solution. So we know, as we have seen before, that since that should be the maximum lambda, this maximum lambda has to be equal to 1, because from this expression we found that the GA has to be very close to 1. So the method that we are going to use is very simple in principle. So we can use the Newton-Raphson method for this characteristic equation. So we start with lambda equal to 1 in order to see when this characteristic equation is satisfied. So we basically perturb lambda until we have a convergent criterion, and so we found our best estimation of lambda that, as I told you, should be very close to 1. Will not be close, will not be exactly 1 for the error sources that we have in W and in V. So lambda close to 1, so our eigenvalue that we have found will be used afterwards in the expression of, so will be the minus lambda, so the attitude matrix, sorry, the K matrix, that we have defined before, minus lambda minus times I, an identity matrix 4 by 4, times the quaternion. So the 4 elements of the quaternions will be found from here, because once we have found the lambda that converged in our Newton-Raphson method, we are able to invert this system, because we have 4 unknowns with 4 equations, and we are able to know the 4 elements of the quaternion. As I told you, lambda, so the criterion of convergence depends, of course, on our requirements, because, for example, you would need the attitude very often, and so you will lead, for example, a faster convergence, so a lower tolerance. So what it means that if you are not converging lambda to the maximum value that you would need, probably you are providing a quaternion with errors that are only given by numerical errors. But the advantage is that you can update your quaternion many times, so you're able to have a faster solution. On the other side, maybe your need is to have a faster, a more accurate solution. So you need to increase your tolerance, so decrease your tolerance, let's say 10 to the minus 13. And once the lambda is converged to that value, you are able to provide the best knowledge of the quaternion, and so the solution that is most accurate. So this is the method that we are going to use. However, as I told you,
prof.
Yes.
Ma una domanda, come facciamo a essere sicuri di convergere proprio al lambda massimo? Essendo un'equazione di... Cioè, teoricamente abbiamo un'equazione di quarto grado, come facciamo a essere sicuri di convergere proprio al nostro lambda massimo?
Okay. So the question is how we're able to be sure that we are converging to the maximum lambda. So in this case, I proposed a numerical method that is called the Newton-Raphson that has the possibility to give you the possibility to know if you are converging or not. Since you are starting from lambda equal to 1, so of course these numerical methods can always be affected by numerical problems. What I mean is that if you start, for example, from lambda equal to 0, I'm pretty sure that you will not be able to converge. You will provide, maybe you can converge to a lambda that probably is not the lambda that you are looking for. But since we know that lambda, so the maximum possible value is 1, what the method does is that it's going to change lambda in order to solve the characteristic equation. And the maximum number should be something that will be lower than 1. So basically your method is starting from 1, going lower, lower, lower. So you're sure that the first value that you're going to encounter will be the maximum lambda, because all the other eigenvalues will be lower than the maximum lambda. So the trick here is that you're starting from lambda equal to 1, and so you know that the maximum value of the eigenvalue is indeed very close to 1. The story would be different if you start from a different lambda, because in that case, probably you will converge to another eigenvalue. And so in that case, the solution will not be accurate. Here, the advantage is that we know that lambda, the maximum lambda of the characteristic equation, should be very close to 1. So basically, you already know your answer. The main problem is that you don't know how far you are from 1, because basically it means that if you have the lambda is very lower than 1, looking at the VABA problem, it means that you have very high errors in W or in V or in both. So basically, the instability of your convergence could also be given by the error in your measurements. But usually your measurements are basically weighted with these parameters. So the sensors with lower delta W, for example, are overweighted. So you are able to avoid these problems because you are considering that some of the sensors could be more accurate. So the trick here is that the lambda, the maximum lambda, you are starting basically with a larger value of the maximum lambda, because for the in ideal case lambda could be equal to 1, but since you have errors, the Newton-Raphson method is going to go down, 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 and the first value that is going to approach, it will be indeed the maximum lambda. So the lambda equal to 1. So hoping that that answers your question, but if you still have any doubts, I will answer your questions also during the break. But I would like to start this part, and also before going to this part, I would like to let you know that I noticed that one of the slides that you have in the previous PDF is not consistent with the KLS table that is reported. So if you want to do some exercise with quaternion multiplication, and you want to obtain, for example, the multiplication of these two quaternion, I updated this expression. Just to let you know, the expression that you have in slide 17 is not incorrect. But basically it is based on a different formulation of the matricial form of the quaternion. The only reason why I reported this updated slide here is that this formulation of the matricial form of the quaternion is consistent with the Calais table that you have in page 16. So if you do the matrix, so if you multiply this matrix by the column vector of E, F, G, and H, you will have exactly this expression here. But as I said yesterday, what I would suggest is to use this formulation in matricial form. That would be exactly the same, but it is more general, and it is usually used in attitude determination problem. So just to recap, this is the first 3x3 elements are the fourth, so the scalar part of the quaternion times the identity matrix 3x3 minus the skew antisymmetric matrix, so minus the skew antisymmetric matrix of the vector part of the quaternion. The this 3x1 vector is the vector part of the quaternion. This one is the scalar part of the quaternion, and this is minus the transpose, so it is a 1/3 vector, because it's the transpose of the vector of the quaternion. So I would suggest to use this one, but if you want to use the other formulation in order to be consistent, use this one. So I will upload this formulation as well. So that will clarify all your doubts about quaternion multiplication. But so let's go back to what we started yesterday. So yesterday we started to look at one of or the main sensors that are used in attitude determination, the star trackers. So today what we are going to do is to provide details of the instrumentation itself. So design performances that will be useful not only for your attitude determination problem, but for your general understanding of the instrumentation. Because when you're going to deal with realistic missions, that could be Earth or planetary missions, you will have to deal with these sensors. And the design of these sensors is very important. And probably few of you could also be part of the team that will design these instruments. So you need to know, for example, the few properties of the stars in order to have a comprehensive understanding on how to design this instrumentation. So the first part of the lecture that we have today is a brief introduction to how to catalog stars. So the main advantage of star trackers is that you have always a very large amount of stars in your field of view. So you are able to use all those stars as a reference point to determine your transformation from the optical bench frame to the inertial reference frame. The main problem is that you have probably too many objects, and this instrument can suffer from ambiguities. So that's the reason why you have to know pretty well how the stars, so the properties of the stars. Because when you are going to look at the star at the sky, you need to basically select the number of celestial objects that you want to include in your analysis. The two main properties that you have to include in your design are the magnitude of a star and the spectral type. So when you look at the sky, you can already see that basically you have stars with different magnitudes. In order to use the proper magnitude, what we are going to use is not the absolute magnitude of a star, but the magnitude that is defined in these slides. So what we are going to introduce is the apparent magnitude of a star. So what we this magnitude is defined by using the information of the flux of the star that is received at Earth. So basically, that's the reason why it is a relative measurement, because you are going to compare the flux that is basically the Earth is receiving for a certain star, divided by the flux that you have from a reference star. Historically, the first star that was used was the North Star, so the Polaris star. But the problem with the Polaris star is that the flux, so these the magnitude of the star changes over time, and so the reason why the star that now is used is Vega. So the flux of the star received at Earth is scaled by the flux from Vega, but it's not a pure. So you're not dividing the two flux. You are doing the logarithm of that. So This is a logarithm scale, and you need to take into account this kind of magnitude definition in order to catalog your star in a certain way. So the magnitude that we have here is called with lowercase m. When you see uppercase m, this is the absolute magnitude. The difference with absolute magnitude is that all the stars are basically ideally considered at the same relative distance of 10 park seconds. 10 park seconds means 32.6 light years. So basically you are locating all the stars at that distance, and so you are taking into account that all the stars are all the stars magnitude is not scaled by their distances. Indeed, what you have here, this lowercase m, depends not only on the flux that is emitted by the star, but also depends on how far the star is from Earth. And the other thing that matters is indeed, for example, that the stars, the flux is, for example, so part of the flux is absorbed by interstellar medium or something that indeed can decrease the flux that is received from Earth. So the reason why we are dealing with the lowercase m, so the apparent magnitude, is indeed that what we need to know is the magnitude that we are receiving at the sensors. So we don't need the absolute magnitude, but this value. Here I referred, for example, the magnitude that you can see are large, so lower in modulus, so lower is the value, the negative value, larger is the magnitude. Since you can see there is a minus 2.5. So for example, the sun is minus 26.8. Although you see very low differences, as I said, this is a logarithmic scale. The other important properties of stars that you have to know when you design a star tracker is not only the magnitude, but is also the spectral type. So all the another way to distinguish between two stars is indeed the spectral emissivity. So at what frequency the star is emitting. In order to catalog these stars in different spectral type, there are 9 categories. So these letters here, O, B, A, F, G, K, M, L, T. Each category has a subgroup of other 10 subgroup categories. So you have 10 by 9 categories. Why you need to have this very tight catalog of stars? Because when we are going to introduce how the star tracker works, you're going to see that the main problem of star sensors is indeed the ambiguity when you are tracking or acquiring a star. So what you need to do in principle is that you have the knowledge of the position of the star from the catalog. On the other hand, you have that your sensor is looking at the sky and is trying to compare what basically is acquiring from its sensor to that catalog itself. So since you can have too many objects in the field of view, the best approach is indeed to provide few properties of the stars that enables to select the object that you want to observe. That's the reason why you are going to look at magnitudes and spectral type. If you are able to categorize these two, so the stars in these two subgroups, you are able to provide a better definition of the stars. That will be fundamental what we are going to see next. For example, here is reported how the different stars categories are reported with respect to the spectral type and the absolute magnitude. A similar plot could be done with the lowercase m, but what you can see here is indeed you have different kinds of stars at different magnitudes, but also a different spectral type that comes from the ultraviolet, visible, and blue, also up to red, but usually this is the range that is used in star sensors. These tables that are reported afterwards are only for your better understanding. You don't need to know the properties of the stars, but it is useful for you to know what are the properties of, for example, the 10 brightest stars in the sky that can give you an idea on how those can be classified. So because the main problem here, we need to classify stars. Because if we are able to classify stars, we are able to design the star tracker in a way that when it's going to look at the sky, is going to use the stars that it needs. We are going to see indeed that the star trackers are not only given by a sort of telescope that basically needs to detect the stars on a detector, but there are also filters that enables to, for example, look at all the stars at category A, for example, spectral type A, or all stars at category or spectral type B. This is important to avoid ambiguities, as we are going to see later. So what you're going to see here is that these stars are distinguished in spectral type and upright magnitude, but also you can find the celestial coordinate of the star. The celestial coordinates are reported in the with respect to the equatorial vernal equatorial plane. So, for example, the two coordinates that are usually used are the sidereal hour angle, that is the angle of the object that you're looking at, and the vernal equinox. So this angle is computed, so is determined on the, I can briefly this, so if this is the equator, you will have that this is the vernal equinox, this is your SHA, okay? It's only for your knowledge. Declination is, of course, the angle above the equator, the vernal equator. Okay, so this is the declination. But this is only for your knowledge. It is important in the design of star trackers. Okay, so this table is also providing you some information. I don't want that you are going to know. It's only for your curiosity. This table informs on the number, the percentage of stars that you have with respect to the magnitude and the spectral type. This is really important when you want to design an instrument. Because, for example, let's assume that our star tracker has the possibility to gather information, so to collect to track stars with the magnitude that is lower than 2.0, okay? So what it means is that you are going to use a filter on your star tracker, for example, a filter that enables to look at this spectral type, because here you have the greatest number of stars in your field of view. So usually when you are able to track stars with this magnitude lower than that, so remember that lower is the magnitude, larger is the luminosity of the star, basically. So you are able, if you are able to have a magnitude that is larger, means that you are able to detect stars with a faint luminosity. So basically that are or very far, or basically that have a very low flux. So you are not able to distinguish them really well. So usually you have also a range in magnitude that you have to take into account. So assuming that your threshold is 2, so you are not able to see any stars with magnitude larger than that, a possible range of frequency that you want to look at is, for example, the stars of spectral category, spectral type B. Because you will have, for example, from 40 bright stars, you have 15, okay? Because it's the larger percentage. This is another similar table that show you that if you are able to look at the apparent magnitude larger than a certain value, so for example from 3 to 8, you will have a number of stars that is larger, because of course you are able to detect stars with also lower that are emitting a lower flux with respect to us. So if you are able to, for example, have a sensor that enables the detection of stars with apparent magnitude lower than 5, if you have a certain field of view, you are able, for example, with the 20 by 26, 227 square degree field of view, you are able to detect, for example, 27 stars of this kind.
So I have a question.
Yes.
Is it common that missions set their star tracker apparent magnitude with a lower value or a higher value? Because if you're trying to minimize, or you're trying to
Yes.
Organize how much, what you're tracking, the higher you set it, the more stars you're able to track.
Yes. So this is a correct question, of course, because actually you are trying to determine which is the threshold that you need. Of course, usually the possibility to determine to basically detect a star depends on the technology. So usually you have intrinsic limitation of your detector. So you have detectors that are not able to detect stars with apparent magnitude larger than a certain value. But also there is another problem, because, for example, there are detectors that are able to detect stars at a certain apparent magnitude, but the error in for example, in the determination of the apparent magnitude could be larger. So it's always a trade-off. So you want to have the larger apparent magnitude in order to have the larger number of stars in your field of view. But on the other hand, you don't want to have a larger you'd want to basically have a detector that basically can provide you error that can provide indeed more perturbation to your measurements rather than benefits. So it's a trade-off, of course. Furthermore, if you have detectors that are able to detect much more stars, they would also require a very expensive computation, because you need an onboard software that is able to process many stars. And so the complexity of the instrument, it is basically it basically relies on these kind of properties. So usually the quality of your measurements is indeed is tuned in order to have the best accuracy and the low complexity of the instrument. So that's the reason why there are different kind of star trackers, because, for example, you can have missions that don't require the attitude determination at the level of micron arc seconds. And so you don't need to look at stars with a very large upper magnitude, but you need, for example, to have to be able to track stars with a certain upright magnitude. And so the complexity of the instrument will be scaled for that need. On the other hand, if you want to improve your knowledge of the attitude at those requirements, for example, a few micron arc seconds, at that point, probably you would need a finer detector, so something that is going to have a better acquisition of stars. So it's always a matter of the complexity of the instrument that you need. So there is no always one unique answer. Depends on the complexity. There are star trackers that are they are designed for example, Earth missions that do not require, for example, just a few arc seconds attitude determination accuracies. But for planetary, probably you need to have much more accurate measurements. Also, basically, that depends on the portion of the sky that you're looking at, because as we are going to see next, and probably in the next hour, is that what we need to do is to know what kind of portion of the sky, so what portion of the sky we're going to look at with our instrument. So the properties of the filters, so what kind of spectral type we're going to look at, and what kind of magnitude of stars we are going to be limited to, depends also on the portion of the sky that we are going to look at. And so what we're going to see is that the main problem for star tracker is indeed that we need to have a preliminary knowledge of our attitude. So usually when you are designing a mission, for example, an interplanetary mission, you know that star trackers are going to look at a specific portion of the sky during cruise. So when it is transferring from a planet to another one, but when it is approaching a planet, let's say Mars, in that operational mode, it will also scan the sky in a different way. So the main problem will indeed have a catalog of stars So the knowledge of the relative position of the stars, or the relative orientation of the stars, at the beginning of the mission. So what we need to know, what we need to load on our system is a fine catalog of the stars. That's the reason why when the star sensor is starting to operate, we need to have a preliminary knowledge of the spacecraft attitude. The reason why we need that is that when you have, for example, you have that this spacecraft arrived at Mars, and the star sensor is now operating in orbit around Mars. So it's going to look at the different portion of the sky with respect to what was looking at when it was during cruise. So the star sensor has to start operating in that time frame. And if you don't have a good preliminary knowledge of the spacecraft, when you load your star catalog, you are loading a map of the sky that is not the part of the sky that you are looking at. So when you are trying to match what the star sensor is looking with the star catalog, you don't have a good match, or probably you don't have a match at all, because basically you are so affected by the errors. That's the reason why we are going to introduce the gyroscopes, because gyroscopes, although are less precise than star sensor, has the advantage to provide continuous measurements. So measurements continuous over time. Let's redo the example of the spacecraft from cruise to orbit around Mars. The gyroscope is an inertial sensor, so it is going to give you the angular velocity of the spacecraft over time from the cruise to the orbital phase. So if you have that information, you're able to reconstruct the attitude of the spacecraft and have a good preliminary knowledge of your attitude. So you have a preliminary knowledge for other instruments, for example, the gyroscopes, that enables to upload the star catalog in the right portion of the sky. Because as we're going to see after the break, the correct load of the star catalog is fundamental for the next step in the star sensor attitude determination software. It is called star identification and acquisition. And so the definition of magnitude and spectral type of the stars, it is fundamental, because if we have the sensor that was designed with specifics properties, we are able to detect the stars that we need to determine the attitude. So the first guess of our attitude determination. So let's have a break here. And we're going to have so 10 minutes break, and we are going to start in 10 minutes.
Sorry, Prof.
Prego, prego.
Can you repeat when we have a gyroscope instead of a star catalog?
Okay, so there will be so I will start the lecture afterwards. But what I was saying is that when you need to start the first acquisition of a star sensor, you need to have a first knowledge of the star position. So what it means is that let's assume that you are in orbit around Mars, and for the first time you need to operate your star triggers. If you don't have any knowledge of your spacecraft attitude, you are not able to load the star catalog because the star catalog give you the position, so the relative orientation of the stars that should be seen by your sensor. So the star catalog has to load the portion of the sky that the spacecraft is going to look at. Okay, so the reason why you need the gyroscopes is because from two different operations of the star trackers, you don't have any information of the attitude from the star trackers. So what you need to do is to have information about the attitude evolution over the two periods in which the star sensor was working. If you have this continuous determination of the attitude, when you restart your star sensor, you're able to load the catalog, so the portion of the sky that you are looking at with your instrument, correctly. And that will be clearer later. If you are loading the correct portion of the sky, you are able to identify and acquire the position of the star. And that is the first step that we're going to see in after the break.
So these boxes are sequential.
So these are the main 4 steps of how the software of a star sensor work. So you will, at the beginning, have the loading of the star catalog. Afterwards, you have the star identification and acquisition. So it means that once you loaded your map, you are acquiring the first measurements, trying to match what you're seeing from your instrument to what it was loaded by the star catalog. You match the two, so you identify the stars. Once you have detected the stars that you want to use for your attitude determination, you use the star tracking. So you don't need to redo the first 2 steps, but you can directly track the stars and do the last 2 steps. So star tracking and attitude processing and refinement. But that will be clear later because it is the second part of the lecture.